today's video, we're going to continue with more examples on geometric sequences. So for this first example, we're looking at a basketball team and they're playing a single elimination tournament. And that means for all the games at each round, the winning team advances and the losing team is eliminated. So it says the committee wants the winner to play 4 games. How many teams should the committee invite? So some of you might already know the answer, which is great. And then you also need to go ahead and write down your explicit and recursive rules. So first of all, I'm going to let n represent the number of games. And I'm going to let f of n represent the number of teams required. All right, so let's think about it. Let's say if we're looking at a function in terms of one game being played, then that means if one game's being played, then I would need 2 teams. All right, so I'm going to go ahead and write my sequence as a list. If I wanted to look at 2 games being played, right, then that would require that I would have 4 teams that are required. Okay, and then I would keep going. And so since this is a geometric sequence, I know what my first term is. Remember, if you're ever trying to figure out your R, you can take the second term. So I can take f of 2, and I can divide it by f of 1. Or some of you guys can see they're just multiplying by 2. But if you couldn't, 4 divided by 2 is 2. So for my explicit rule, I'm going to say f of n equals the first term, so 2, times 2 to the n. Okay, and now I need to determine, is it n or is it n minus 1? Well, we started off with 1 game, so it's going to be minus 1 for n greater than or equal to 1. And for recursive, we're going to say, all right, f of 1 equaled 2. And then the rule is that f of n equals the r, so 2 times the previous number for n's greater than or equal to 2. So if that's a 1, that's a 2. And there's my second rule. All right, let's look at, you have an online video game tournament and it begins with 1,024 players. 4 players play in each game, and then in each game there is only 1 winner and only 1 winner advances to the next game. So how many games will the winner play? Okay, so let's organize our information. So let's say that n is going to represent the number of rounds. And then let's let f of n represent the number of games played that round. Okay, so if we think about the first round, there are 1,024 players, but keep in mind that there are 4 players in each game. Okay, so we're going to divide this by 4 players each game, and so that's going to tell me that we're going to have 256 games going during the first round. So the first round is 256. Okay, so then if we want to try and figure out, well, what's their common ratio, it says only one of the winners from each game is going to advance. So remember that there were 4 players, and so only one of those 4 players is going to advance. So that's our common ratio, is 1/4. Okay, so we're going to basically be multiplying this by 1/4. So for our explicit rule, okay, we're going to say f of n equals our first amount of games. So we had at first, we have 256 games going during the first round, times the common ratio, which is 1/4, because only one of the 4 players is going to advance. And I'm going to say to the n minus 1, since we have a first round, for n's greater than or equal to 1. And then for my recursive rule, kind of running out of space here, So for my recursive rule, I'm going to say f of 1 is 256. And then I'm going to say f of n equals the common ratio times f of n minus 1 for n's greater than or equal to 2, because 2 is bigger than 1. All right, let's look at the next one. So it says you have two biological parents, you have 4 biological grandparents, 8 biological great-grandparents. So we want to know, like, how many direct ancestors do you have if you trace your ancestry back to 6 generations. All right, so again, if we wanted to look at this, we're starting off with our 2 biological parents, then we're looking at our 4 grandparents, then we're looking at our great, okay, and then it just keeps going. All right, so it doesn't necessarily tell me which one to write this in. So let's go ahead and just write this one in explicit. All right, so we're going to say f of n equals our first. So we're going to say 2 times our common ratio. So remember, the ratio is the second term divided by the first. So our common ratio is they're multiplying by 2 every time. Now you guys need to say, is this n or is it n minus 1? Well, because we're talking about the first generation of parents, so that would start off at 1. So we'll say n greater than or equal to 1. So then it says let's talk about 6 generations back. So let's plug in a 6, which equals 2 times 2 to the 5th, which equals 2 times 32. So there are 64 ancestors. Okay, what about if you go 12 generations back? So if you plug in a 12, we're going to say 2 times 2 to the 12 minus 11. So we're going to say 2 times 2 to the 11th. So 2 times 2 to the 11th. So we get 4,096 ancestors. All right, let's look at this one. All right, so Sierpinski is a designer, and he included fractals, and so what that just means is that you're doing a repetition. So he would take a geometric figure, shade it in, and then he would start removing the shading to create a fractal pattern. So the Sierpinski carpet is a fractal based on a square, and then in each iteration, the center of each shaded square is going to be removed. So it says, given that the area of the original square is 1 square unit, enter the sequence for the area of the nth iteration of Sierpinski's carpet. So the first iteration is the original square. All right, so if we want to look at, so we've got the first one is a 1, but then we need to look at our common ratio. Okay, so if I wanted to look at this, and I'm trying to, I don't know how well you guys can see that, trying to show you all the little squares here. Okay, on the second square, how many are shaded? So we've got 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 of the 9 original squares left. So this is my common ratio. Okay, so if I took 1 times 8/9, I would get 8/9 of the squares being shaded. Now here, you could put a 1 out front for the first term, but it's not necessary. Okay, and then my common ratio is 8/9. 4 n's being greater than or equal to 1. And now for whatever reason, HRW kind of like shifts this. So again, like f of 1 equals, so in the first square it was 1 full shaded square. And then my rule is going to be the common ratio times the previous number. So I'm going to say 8/9. Okay, and again, since this was a 1, then that means my n's on recursive needs to start off at a 2. And then it says find the shaded area after the second iteration. Well, you can count that. Okay, and it says then round to the nearest thousandth. Okay, but let's say it was something other than one of these that you didn't want to count, and you're definitely not going to want to count all of that. But you would plug it into your explicit. So you would say f of n equals, I could say the first term, which was 1. It's not necessary to have the 1. And then if I wanted to put in 2 minus 1, okay, so that's just going to be 1 times 8/9, which again, we already knew that it was 8/9. But it just wants you to write that as a decimal. So 8/9 to the nearest thousandths. Remember, it's tenths, hundredths, thousandths. You guys can't see that. Let's try that again. Tenths, hundredths, thousandths. But you always want to look at the number behind. And if it's 5 or bigger, it's going to bump that up. So we're going to say 0.889. Okay, so pay attention to your rounding. All right, let's look at these last two examples. Given the sequence, predict the 33rd term. So remember that if they're wanting you to predict a higher term, use an explicit rule. Explicit rules allow you to find nth terms. So I'm going to write my explicit rule. I'm going to say f of n equals, and I'm going to say that we have our first term, which is 16. Okay. Times my common ratio. So I'm trying to figure out what are they doing from here to here, here to here. Okay. So again, you can always take the second term and divide it by the first term so that you get 1/2. Now I should have made a table. We're going to use this as a 1. Okay. So then this will be n minus 1. All right, so then now that I have my rule, I can say f of 33 is going to equal 16 times 1/2 to the 33 minus 1. All right, and then again, we always want to be careful when we're typing things in. So I'm going to type in 16 times 1/2. And I'm going to put parentheses around this just so my calculator reads it correct. 33 minus 1. Okay, so we get a crazy, crazy small decimal. So that means I need to move that decimal place over 9 spots. So I'm going to move it over 1. And then I need 8 more zeros in front of it. So we get 1, 2, 3, 4, 5, 6, 7, 8. And then we had the 3, 7. So I'm going to round the 3, 7. We'll just leave it at that. Didn't tell you how to round. All right, let's look at this rule. We're going to write out the first 5 terms. So again, remember that this is your first term. And this is what they are multiplying by. So the first term is 1/2. And then we're going to take 1/2 times 6, and we're going to get 3. We're going to take that times 6, and we're going to get 18. We're going to take that times 6. So what is that? 108. We're going to take that times 6. So that's, what, 648. And there's my 1, 2, 3, 4, 5 terms. Okay. Looking at the next one, they're saying that you're starting off with the first term at a 10. And then this is going to be our multiple. All right, so I'm going to take, and you could think of 2/10 as like the same thing as 1/5. So I'm going to take this times 2/10, okay, or times a 1/5, okay, which is going to give me 2. I'm going to take this times 2/10. Okay, so that's going to give me 2/5. I'm going to take this times 2/10. So that's going to give me 2/25. 1, 2, 3, 4. So we need to go one more. We're going to take this times 2/10. And that's going to give me 2 over 125.